Hi, today I will present my final project on marketing mix modeling, or MMM, and revenue forecasting, developed as part of the dynamic modeling forecasting in big data course in the Harvard Masters in Data Science program. The objective of this project is to estimate the impact of marketing channels on revenue, improve revenue forecasting, and identify opportunities for budget optimization using a robust model comparison framework. The project starts from a common marketing problem. How do we know which channels drive revenue, and how should we allocate budget? A key motivation is that many MMM implementations depend on one model specification, which can create model risk. My research question is how to estimate channel impact and optimize budget allocation using a robust framework based on model comparison. The dataset comes from the Meta Robin demo and the Deutsche Bundesbank and contains 280 weekly observations, which is approximately 4 years of data. The target variable is revenue, and the country is Germany. The main predictors are spend across 5 paid media channels, along with controls such as competitor sales, newsletter, Germany's weekly activity index, events, trend, holidays, and seasonality. The trend, seasonality, and holiday were decomposed using Profit package from Meta's open source. Exploratory analysis shows clear seasonality and trend in revenue, as you can see in the chart on the top at the left. Media variables are skewed and often sparse, as you can see in the histogram and the bottom left, which motivates for log transformations. The autocorrelation and cross-correlation plots, as you can see on the left, suggest that past marketing spend can influence current revenue, which motivates for lag variables. These exploratory findings directly inform future engineering. The modeling framework separates two complementary objectives: attribution and forecasting. Attribution models are designed to estimate and interpret the contribution of marketing channels to revenue, while forecasting models focus on maximize predictive accuracy for future revenue estimation. This distinction represents an important innovation of the framework, as many traditional MMM approaches rely on a single model specification for both interpretation and prediction, despite the trade-off between interpretability and predictive performance. To address this, the analysis evaluates multiple model families, including linear regression, ridge regression, time series model, and machine learning approaches. Baseline model used only contemporaneous media spend variables and serve as benchmark specifications. Level models incorporate raw media spend, lagged effects, and control variables, while log models apply also logarithmic transformations to capture diminishing returns and saturation effects. Among the forecasting approaches, VAR and state space models are used to capture temporal dependencies and underlying trends, whereas machine learning models such as GBM and random forest focus on non-linear relationships and predicted performance. Rather than rely on a single specification, all models are compared systematically using out-of-sample validation performance based on R-squared, which measures how much of the revenue variation is explained by the model, and normalized root mean square error, which measures prediction error relative to the scale of revenue. Models are trained on the training set, evaluated on the validation set, and the final select model is reported using the holdout, the test set. The validation results shows that Ridge log and OLS log perform very well. Ridge log is selected as it's the best model. Moreover, it gives a better balance between accuracy and interpretability. In marketing mix modeling, interpretability is critical because the model is used to estimate channel contributions and support budget decisions. Ridge also helps address multicollinearity, while log transform variables capture diminishing returns. So the Ridge log model has a strong predictive performance on the test set, achieving an R-squared of about 0.91 and a normalized root mean square error of about 1.133, as you can see in the table. The actual versus predicted chart shows by the plot on the right at the top, shows that the model captures the main movement in revenue, although some deviations remain during sharp changes. This confirms that the model is useful for both forecasting and decision support. Residual diagnostics show no systematic pattern over time, as you can see in the chart at the bottom right, and no structure against fitted values, indicate that the model captured both temporal dynamics and functional relationships well. Additional text was made, including the distribution of residuals, Kiki plot, and autocorrelation analysis that do not reveal any major violations of model assumptions. Overall, this supports the reliability of the model's estimates. And last but not least, the coefficient estimates, and as you can see in the chart at the bottom left, indicate that the external control variables, particularly the event indicator and the weekly activity index, contribute substantially to explain revenue variation. However, the event variable occurs only a few times throughout the sample, and therefore should be interpreted cautiously, as sparse indicators may absorb disproportionate variation and behave similarly to outliers. Marketing variables exhibit both contemporaneous and lagged effects, suggesting that advertising impacts are distributed over time and reflect carryover dynamics across channels. The ROAS estimates, computed using the training validation periods, measure the ratio between incremental predicted revenue and marketing spend for each channel. Specifically, channel contribution was estimated by comparing model predictions under the observed spend levels against a zero spend baseline scenario for the specific channel, while holding all other variables constant. Results show substantial difference across marketing channels, with Facebook and search exhibiting the highest returns relative to spend, while out-of-home generates comparatively low incremental revenue despite higher investment levels, indicating lower efficiency and saturation effects. Response curves were generated by varying the spend of one channel at a time, while all other variables constant, allowing the model to estimate the corresponding change in predicted revenue. The resulting curves clearly demonstrate diminishing returns, where additional spending produced progressively smaller incremental revenue gains, particularly for TV at the higher spend levels, as you can see in the chart. These findings support the use of log transformations in the model and provide the foundation of budget optimization and scenario analysis. The optimization scenario reallocates 10% of the total media budget from the lowest ROAS channels, out-of-home and print, to the highest ROAS channels, Facebook and search, while keeping total spend constant. The reallocation was evaluated on the test period by generating counterfactual predictions under the new budget distribution and compared them to the baseline forecasts. Results indicate that an increase in expected revenue of approximately $54,000 without requiring additional investment, demonstrating that the value of reallocate spend toward more efficient channels identified by the model. The results were also compared with a selected meta-robbing model. Robbing activity slightly lower NRMSE, while the RigLog model produced a higher R-square, suggesting comparable predicted performance, but different modeling philosophies. Robbing emphasizes automated decomposition and parameter optimization with a single framework, whereas the present approach prioritizes robustness through model comparison and explicit feature engineering. So to conclude, the project shows that marketing channels differ meaningfully in efficiency and that diminishing returns and lagged effects are important. The selected RigLog model provides a practical balance between interpretability and predictive performance, and the budget optimization shows that better allocation can improve revenue without extra spend. But just make sure that it's not causality here, it's just a relationship between features with the revenue. More broadly, the project demonstrates that the model comparison can make marketing mix modeling more robust and can be used in conjunction with open source models as Robbing. Thank you very much.